Previously, we've covered some simple probability distributions. Now in this section, I'd like us to move on and consider the concept of expectations. So remember we said about decision making under uncertainty, we have to make decisions now not knowing exactly what's going to happen in the future. So the best we can do today is form an expectation about what we anticipate would happen in the future. So let's revisit the case of rolling a fair die. So previously we saw the both tabular and graphical form of that probability distribution, i.e. all possible outcomes of that experiment, and assigned to each value its probability of occurrence. So in advance of rolling the die, what would we expect to be the outcome? So up till this point, we've just looked at the distribution, the probability distribution as a whole, and now I'd like us to focus on one particular attribute of that distribution, i.e. what is the expectation? On average, what score on the die do we think is going to occur? So we're now going to consider the concept of a mean, an expectation, an average. We can use these terms synonymously, i.e. interchangeably, to represent what is the expected score on this die. So we see those 6 possible values, 1, 2, 3, 4, 5, 6. So what we're going to do is to take a probability weighted average, i.e. we consider each possible value of the variable, 1, 2, 3, 4, 5, 6, and assign to each of those a weight, reflecting its probability of occurrence. Now in the case of a fair die, of course, these weights are going to be equal, because we said for a fair die, each of those 6 scores was equally likely to occur. So the way to construct, or indeed calculate, this expectation of x, the expected score on a die, is to take each value of the variable, multiply it by its probability of occurrence, and add them all together. So what is the expected score when we roll a fair die? It will be 1 times a sixth plus 2 times a sixth, etc., up to 6 times a sixth. Now, if you want to type those values into your calculator, you will come up with an expectation of 3.5. So what this is saying is that your expected score when you roll a fair die is 3.5. Now, of course, we know you would never roll 3.5 when you roll that die. It was not a member of the sample space. It was not a possible outcome of this experiment. So how should we interpret this concept of an expectation? Well, let's imagine you did this sort of relative frequency experiment. You took your fair die and you rolled it, not once, but a very large number of times. Let's keep the numbers simple. Let's assume you roll this fair die, let's say 600 times. Then one would anticipate approximately 100 times out of those 600, a 1 would be the uppermost face. Roughly 100 times it would be a 2, 3, 4, 5, and 6. So if you now consider the average score across those 600 rolls of the die, you would get a value of approximately 3.5. I say approximately because it's pretty unlikely you would roll exactly 100 1s, 2s, 3s, 4s, 5s, and 6s. So the expected value, this probability weighted average that we had calculated, I'd like you to view this as a long run average, such that if you roll this die a very large number of times, the 3.5 is, we would call it a measure of central tendency, a measure of location, i.e. the value that we tend to get on average, even though the 3.5 itself is not an attainable value by itself. Let's consider another example. Let's go back to tossing the fair coin. So there we said the outcomes, heads and tails, were not numeric, but we could easily apply some simple binary coding, let's say 1 for heads and 0 for tails. And assuming this fair coin, then we have a 0.5 or a 50% chance of each of those outcomes. So what would be the expectation for the score on the die here? Well, we take each value of that variable, 0 and 1 in this case, and multiply it by its corresponding probability of occurrence. In this case, these equal weights of 0.5 and 0.5. So 0 times 0.5 plus 1 times 0.5 will give us 0.5. So there is our expectation in this for this simple probability distribution. Now you might argue 0.5 has no sort of real world meaning in the sense of tossing this fair coin, and I'd perhaps agree with you on that point, but nonetheless that methodology of calculating an expected value remains the same as in the case of the fair die. So let's consider one more example. Suppose you're feeling lucky and you head down to the casino, and let's suppose you're interested in roulette. So you go to the roulette table, and the casino offers the following game. Namely, you bet £1, $1, €1, whichever currency you prefer, such that if, when you spin the ball on the roulette wheel, if a red number comes up, you get that £1 stake back, but you also get winnings of £1. If you don't get a red number coming up, you lose that stake of £1. Now, roulette wheels do vary in different parts of the world. For our example here, we'll consider a roulette wheel with 18 red numbers, 18 black numbers, and 1 green 0. So thinking back to our previous session on some simple probability distributions, let's assume this is a fair roulette wheel, such that when you spin it and the ball bounces around, it's equally likely to land on any of those numeric slots on the roulette wheel. So if we have 18 red numbers, 18 black numbers, and don't forget that green 0, that would mean we have 37 equally likely outcomes when we spin this roulette wheel. So let's come up first of all with our simple probability distribution, and from then I'd like us to calculate the expected value and think about the real world meaning of this as well. So our experiment, we roll or spin the ball around the roulette wheel and consider what the outcome is. So if we take things from the perspective, let's say, of the casino, sometimes called the house. So what will happen? When the person stakes the pound, dollar, the euro, one of two things will happen. The ball will spin, and if that ball lands on a red number, then the customer wins £1 from the casino. And of course, that would reflect a loss from the house's or the casino's perspective. So let's say in this experiment, one possible outcome is the loss of £1, -1 from the casino's perspective, if a red number comes up. Of course, the other possibility is that it's not a red number, which means either one of the 18 black values or the green 0. And in this case, the casino gets to keep the stake of the customer, and hence it makes, if you like, a profit of +1 pound, dollar, or euro. So if we write out this probability distribution, from the casino's perspective, there are two possible outcomes: loss of -1 if it's a red number which occurs, or a profit of +1 if it's a black number or the green 0. So considering the sort of classical approach to probability we saw previously, whereby every possible outcome in the experiment is equally likely. So in this case, these are the 37 different values on the roulette wheel, and we're imagining, if it's a fair game, that that ball is equally likely to land on any of them. Of course, 18 of those 37 agree with the event of a red number occurring. So the probability that the house, the casino, loses this pound will be 18 over 37. Remember the little n over capital N. Number of outcomes agreeing with the event of interest over the total number of equally likely outcomes in the game. Of course, to complete this probability distribution, somewhat trivially, if there are 18 red numbers, all of the other values are either black numbers or that green 0. Of which there are a total of 19 of those possible values. So the probability that the house wins that pound from the customer would be 19 over 37. So let's now work out the expected winnings or potentially losses which are accrued to the casino. So we take each value of this random variable, i.e. the winnings or losses to the house, multiply by the corresponding probability of occurrence and add these together. So there's a loss of -1 occurring with a probability of 18 over 37. So we do -1 times 18 over 37 plus 1, the winnings of a pound, times 19 over 37, the probability that that event occurs. Now, I will allow you to use a calculator to work this out, but I checked this earlier, and the expectation you would get is 0.027. So just like with the toss of or roll of a fair die, where we had an expected score of 3.5, that was not attainable. Similarly here, the expected outcome, this 0.027, could never occur in a single play of this roulette game, because we know the only possible outcomes is that the casino either wins a pound or it loses a pound. But remember the interpretation now of viewing the expectation as a long-run average. So what this means that for every pound that is staked by a customer on this roulette game, the casino can expect to win 2.7 pence. That's a 2.7% gain of all of the money which is staked by the customers. So true, in any one play of this game, maybe the customer is lucky. A red number comes up and the casino makes a loss. But of course, we would anticipate this is going to be happening 18 out of 37 plays, 18 plays out of every 37 of this game. Of course, on average, 19 out of every 37 plays of the game will be good for the casino and it wins some money. So in the long run, of course, the casino sees a positive expectation here. Now, this is no coincidence. The casino operators are not stupid. They design these games such that, on average, in the long run, that the house always wins. Of course, the casino would want customers to win on occasions. If every time someone made a gamble in the casino, they lost money, if there was never any winnings on the customer's part, who would ever go to the casino if it was a certainty that you're going to lose money? So the casino welcomes these success stories on occasions where some people do win lots of money. But of course, for every winner, there are going to be typically more losers, and on average, in the long run, the casino comes out ahead. So a nice section here for us to consider the concept of an expectation. You may also like to relate this back to that Monty Hall problem. You have a 2/3 chance of success if you switch the door, only a 1/3 chance of success if you stick with your original choice. So again, thinking in terms of the long run, as a strategy, if you switch each time, then one is expected to win 2/3 of the time and lose only 1/3 of the time. So in the long run, you would win far more often than you lose. So remember, there are no certainties typically in life other than those death and those taxes. If we can think about forming expectations, we would tend to base the decision-making under uncertainty, but use these expectations really at the heart of our decision-making process.